Hello, my nerdy, geeky, brilliantly chaotic designers, and welcome back to the Geeks Design Studio. I'm your host, Divya Goyal, an architect, certified design tech obsessive, and someone who's absolutely still figuring this all out alongside you. We are on episode 3, season 1, and today's a very special one because I've been genuinely waiting to have this conversation for a while now. You know how sometimes you meet someone and you think, oh, they are doing the thing I didn't even know was possible. That's how I felt the first time I heard about today's guest. She is a computational designer and a researcher. She did her MSc thesis at TU Delft, which, if you don't know, is one of the most important places in the world for pushing the boundaries of what buildings can actually be made from. Her thesis was called Silva, and it involved robots and waste lignin and cellulose. And I'm going to let her explain all of that because I will absolutely butcher it if I try. She co-authored a paper presented at ECAAD 2025 on robotic binder deposition. She's currently working as a computational designer at Architect Company in Rotterdam. She's originally from Turkey and she's been through Bilkent University and TU Delft, and she's one of those people who exists at the exact intersection of material science, machine intelligence, and architectural design. Her name is Cansu Ersoy and she's here. Cansu, hello.
Thank you very much. That was quite the introduction and I was a little nervous by the end of it.
You should be. You're very impressive.
I really am not. I'm just someone who got really into a material and couldn't find my way back.
Honestly, and that's the best origin story. That's how all the best research happens. And so, before we dive into the robots and biocomposites, let's just ground people. And I would like you to give your introduction, the real introduction of who actually Cansu Ersoy is, in your own words, not the LinkedIn version.
Okay, the real version. So I'm someone who grew up in Turkey, and I grew up really interested in how things are actually made. After deciding to study architecture in Bilkent University in Ankara, I started to realize that I really, really do love design, but I kept feeling this disconnection between what I was drawing and what could realistically be built. And this kind of also showed itself during my profession. And that's when I decided to come to TU Delft for my master's in building technology. And that's when the gap really started to close. I was working in labs, experimenting with materials, 3D printing, programming robotic fabrication workflows. And it was the first time that I felt like design, engineering, and actual making were all part of the same conversation.
Gap between designed and buildable, that's so real. We spent years.
Exactly. And nobody really tells you that that's happening. You're just, one day you're in the office making beautiful dreams and designs. And then you go up to someone and you say, okay, here's my design. And they're like, okay, I'm not going to be able to build this. And you're just devastated for the really first time.
First time? Try every other week.
Exactly.
Okay, so now really towards computational design specifically, because you could have stayed in traditional practice. You had office experience, you were at Computational Ersoy Architects. Why the pivot toward the technical side?
Honestly, it was mostly boredom with repetition. And I say that with the deepest respect for traditional practice. But I just kept noticing all this time being spent on tasks that felt like they could be very easily optimized. There is a correct answer. So why are we doing it manually? It was also realizing how much of architecture is based on rules and relationships. So once I started learning Grasshopper, I could encode those relationships directly instead of manually redrawing variations.
And
Yeah.
How your relationship with Grasshopper, how would it hurt you transitioning from your experiences throughout the years?
So the moment I wrote my first parametric script and watched a building geometry update in real time, I did feel something shift in my brain, and that's when I got kind of addicted to Grasshopper. And I really wish that I could have something like Grasshopper in real time as well. And to tell it the rules, the data, the parameters, and it figures out the form. It felt like architecture working out the way it should.
Yeah, that click moment, right? I want to hear more about that because I think a lot of our listeners are sitting on the edge of learning grasshopper or getting into computational stuff and they're terrified. Did it feel natural to you from the start?
Well, absolutely not. Of course, as every architectural software is, it was also a struggle, and I was convinced that I could not do it. I had one script that was supposed to create a simple service, and instead it just made everything disappear. I even had an instructor who really strongly discouraged me to follow a computational design or parametric design route in my career. But there's something that just happens, and I think it's the same with maybe learning a new language, is that it's basically just the syntax stops being something that you have to look up and it just starts making sense to you. It's almost like a math problem. Then you just start to think in that language.
Interesting. So you start to think in it, and that's a beautiful way to put it. All right. I've been waiting for this part. Tell me about Silva. And I mean really tell me, because I've read what I could find, and it's fascinating, but I don't think I've fully grasped what you actually built. Start from the beginning.
Okay, so Silva started from a fairly simple observation, which is that the paper and pulp industry produces large quantities of lignin as a byproduct, and it's basically burned for energy. But at the same time, construction industry is one of the largest producers of waste and carbon dioxide. And we're always looking for lower carbon material alternatives. So what the research explored was whether lignin combined with cellulose fibers could be used as a feedstock for robotic extrusion processes in different scales of architectural applications. The idea was not just to print components, but to experiment with graded material compositions, meaning that the material properties would vary across a component depending on structural requirements.
Okay, so first of all, because not all of our listeners are fully qualified architects or some are transitioning, so I need you to explain graded, because I think that's a part that's not always,
Of course. So I can give an example from nature. Nothing is uniform. A tree does not have the same density everywhere. One tree can very much differ from another one. The outer bark is different from the inner core because the structural demands are different. What we're doing in standard manufacturing is basically ignoring that. We make one material the same all the way through, and then we just use more of it where we need more strength, which is really wasteful.
So we are brute forcing it.
Exactly, brute forcing. But if you can control the material composition during the printing process, layer by layer, you can make something that's strong where it needs to be strong and flexible where it needs to be flexible, using less material overall. So that's the dream of strength-graded biocomposites.
So basically you made 3 different formulations of this material with different strength ratios. Is that what you're saying? And then built a workflow to figure out which formulation goes where in a structure?
Yes, that's exactly it. I tested the mechanical and rheological behavior of each formulation, but to be completely honest, it wasn't a very significant rheological testing because this was merely a thesis project and I didn't have all the time and the budget in the world. But basically what I mean by rheological is that how it flows, which matters enormously in extrusion-based printing, because if your material is the wrong viscosity, the robot basically just makes a mess. And then I worked on that quite a long time. And following that, I built a parametric workflow in Grasshopper, Python, and Karamba that linked the material logic to the design. So the geometry, the slicing strategy, and the robotic toolpaths were all connected to what the material could actually do. We call this a closed loop iterative feedback mechanism.
Right, and that is a very different way of thinking about design, because what I remember from my university days is that most of us design first and then ask material questions, and you're designing from the material outward.
Yes, and that's the shift that computational design actually makes possible, because the material properties, the structural requirements, they just become parameters in the system, in the same system as the geometry. They're not just separate conversations anymore.
Okay, I would like to...
Sorry, what?
So, what was the hardest part? Like the thing that made you want to throw the whole project out the window?
Well, yeah, the hardest part was basically the rheology. It was definitely getting the material behavior right. In extrusion processes, how the material flows is critical, and the viscosity, the printing parameters like temperature, speed, everything will collapse if the viscosity isn't right. So that meant a lot of trial and error in the lab, failed prints, adjusting moisture content, testing different ratios. It's not the glamorous part of digital fabrication, but it's actually where you learn the most.
So even with all the computational power, you still had to get your hands dirty?
Yes, always. That's the part I think that people miss about digital fabrication. The digital does not replace the physical. It makes the physical smarter. But the physical still has to happen. And it's messy and surprising and also humbling in all the best ways.
So here's an opinion round. I'm going to ask you things and I want your real answer, not the professional answer, the real one.
Okay.
First, robotic fabrication actually ready for mainstream architecture or not? What are your thoughts about it? Or is it still a research experiment?
Yeah. In my opinion, robotic fabrication is ready for certain applications, but not yet universally. The robotics themselves are extremely precise and reliable, but the bigger challenge is the material ecosystem. We have robust workflows for materials like concrete, certain polymers, plastics. But if we want more sustainable options, bio-based materials, biodegradable materials, recycled composites, there's still a lot of research needed to make those processes stable and scalable. So to answer your question directly, I think it's not completely ready for mainstream, but I do believe that research is required on every single step of architecture, and that's what makes it grow.
Right. So what I've understood from your answer is that the robot is still ready and in the right direction, but we still need to explore more in terms of the material library side.
Yes, exactly. The robot is ready, material library is not.
Okay. And what about architectural schools? Are they preparing students for the world that actually exists right now?
Well, this is a bit of the controversial one.
I know. That's why I'm asking it.
Well, architecture education is definitely getting better, but there's still a massive gap between what's taught in studios and what's happening in the field. So it gives you a strong conceptual foundation, but the technical side, and specifically the technical side of computational design, often requires a lot of self-learning. And I got to TU Delft and realized that I had almost no fluency in the tools that actually drive computation. The scripting, the material science, the fabrication logic, they had to be learned almost from scratch. And I think a lot of students get to practice and feel blindsided by this gap.
Actually, we talked about this a little bit in our last podcast. And what I think is that you're self-teaching the most important skills in architecture especially. Did you feel that as well?
Yes, completely. Most of the things I learned about Grasshopper, I did, of course, learn about them through self-learning, but also from some of the electives that I was taking. I would watch tutorials at 11 p.m. and everything that I know about robotic programming came from being in the lab and breaking things, figuring out why something happened. And the normal curriculum gave me the conceptual framework, but the actual technical fluency starts when you start troubleshooting that red notification icon on Grasshopper. So yes, self-taught. And I think that's actually okay, maybe if not better. We should be honest about it rather than pretending the degree covers everything.
Yeah, and I really appreciate you saying that because I completely agree with your point of view. I have literally felt and been through the same been in the same boat, because I think a lot of young architects feel like there's something wrong with them and if they're still figuring out. And actually everyone is still figuring it out. And the degree is the beginning, not the destination.
Yes, the degree is the beginning. I love that. Put that on a poster.
Yeah, definitely. And AI in architecture, threat or something else entirely? What are your thoughts on that?
Well, I feel like it's something else entirely. And I think that the framing of threat versus tool is part of what's holding the conversation back. So because when you actually work with AI, and I've started integrating it into my workflow at Architect and also during the end of my thesis, it's not doing the design, it's doing the translation. It's taking something complicated and making it legible faster. It's actually a tool. I think the biggest mistake that a lot of people do is taking it out of its context. So the decision about what to translate and why and what it should mean, that's still entirely human.
Yeah, that definitely is. And that's such a good distinction as well to do. The translation, not the origination.
Exactly. And I think when it starts doing the origination, if it ever does, that's when the interesting philosophical questions really start. But we're nowhere near that in architectural practice. Right now, it's just a very first fast research assistant with no ego whatsoever, which honestly is great.
Yeah, a very fast research assistant with no ego. I think you should put this on a poster. And I want one of those in every meeting I've ever been in. Anyway, so there's a last opinion question. And this one I'm genuinely curious about. A Turkish woman working in computational design in the Netherlands. And the field of robotic fabrication is still quite male-dominated, which I feel I've heard from most of my friends, quite Western dominated. Do you feel that as well? And does it affect how you work?
I feel it. I won't really pretend I don't. There are rooms I walked into where I'd been the youngest person, the only woman, and of course, depending on the context, the only non-European. And that's something you actually feel a lot in Europe. And sometimes that means I just have to work a little harder to be taken as seriously as I should be on first impression. But I really feel that this is important. I've also found that it gives me a perspective that genuinely adds to the work. I approach problems differently. Either it's material or computational. I ask questions that other people in the room haven't thought to ask. And increasingly, I think the field is recognizing that the diversity of perspective isn't just ethically important, it's scientifically valuable.
That's a really important thing that you just said. The second part, and say that louder.
The diversity of perspective is scientifically valuable, not just the right thing to do. Actually, better science.
Interesting. So if silver works, if robotic extrusion of strength created by composites becomes viable at scale, what does that actually change in the built environment? Can you give that idea of the picture?
Yeah. So, okay. Imagine a building material that comes from agricultural or industrial waste, not quarried, not synthesized from oil, not carbon invasive to produce. And because the robot can grade the material strength across a component, you use less of it to achieve the same structural performance. And because it's made from organic matter, cellulose, lignin, biodegradable thermoplastics, it is in principle also biodegradable. You're not producing a building that will sit in a landfill for 300 years when it's demolished. You're basically producing something that is eventually going to return to the ground.
The building that will return to the ground, and I generally got a little emotional just then.
Well, and the other thing is customization at no extra cost. Right now, customized building components are expensive because they require custom molds, custom manufacturing setups. And most of the time, if you did a project with a custom manufacturing, then if anything goes wrong and you need maintenance, you have to make sure that the manufacturer is still manufacturing this item. If not, you need to make sure that you want to replace it. So in the end of the conversation, create a whole different problem. With robotic fabrication, every component can be different because the robot just follows a different path. You can design for a specific site, a specific climate, a specific structural load, and the fabrication process just doesn't care. It just makes what you have designed.
And that's the end of the standard components. That changes everything about how we think about procurement, about supply chains, and about what a building can even be.
Yeah, it changes the relationship between design and making, which is, I think, the most exciting thing that's happening in architecture right now.
Yeah. And I think you're generally very honest about your answers and on point. And there's going to be a final question, and I promise that's literally the final question. What do you want to be working on in 10 years, or let's say 5 years? And the dream project, the thing that would make you feel like you had really done something.
Well, Working in computational design, it's usually really hard to keep up with advancements in technologies. And then all that you see on LinkedIn, I've achieved this, I've achieved that. What I really want to see is a real building standing that uses bio-based materials. It's robotically fabricated components that someone actually lives in or works in or just basically uses it. Because research, in my opinion, is extraordinary. I really love it, but the proof point is the built thing. I want to stand in front of something and say, that wall was made from paper industry waste by a robot designed to perform exactly the way it does. And it works. And that's the dream.
Wow, I mean, that's really exciting. And I want to be the first person to be invited to the opening.
You'll be the first call I make, no worries.
Okay, Cansu, this has been one of my favorite conversations so far. Like, genuinely, I'm not just saying it for the sake of saying it, like, genuinely. And I feel I understand something about materials and robots and future of how we build that. And I didn't understand before, and that's the best feeling I know.
Well, thank you for having me, and I hope you don't say that to all your guests. And thank you for asking questions that weren't scared of the technical side. That doesn't always happen to me.
Always. And okay, before I let you go, where can people find your work and where should they follow you?
Well, LinkedIn is the best place. You can just search my name. And you can also find me on Instagram, where I do sometimes follow up with things at the end of conferences or when I publish something. I share research updates and the kind of things I'm thinking about there as well.
Okay, perfect. We'll link everything in the show notes. And to everyone listening, if this episode made you see materials differently or what you think about what a building could be made from, that's the point, and that's exactly it. Okay, thank you so much. All right, so this was episode 3 of the Geeks Design Studio. I am Divya. Thank you so much from the bottom of my geeky heart for being there. And one last thing, we are actively looking for more brilliant boundary-pushing designers and researchers to come on this show. If you are working on something at the edge of architecture and technology, or if you know someone who is working in the same fields, my DMs are open on Instagram at the Geeks Design Studio. Computational designers, robotic fabricators, AI researchers, sustainable material scientists, digital twin builders, I want all of you. Come find me. See you in episode 4, and until then, stay curious, stay geeky, and build something extraordinary. Thank you.